Greetings, math friends. We are going to take a look at this almost definite integral. And the reason I say almost definite integral is because I have a variable here as the upper bound on my integral. So we're going to go ahead and do this calculation, but with the idea that when we get the integration process going here, we're not really going to have a complete idea of what's going on because our bound on the integral is a variable. Is this useful in some situation? Potentially. Yeah. If you have a situation where you want to integrate something, but you want in the end to have to be able to substitute in a variety of values for that, but essentially it's defined on the same function, then this could have some benefit to you. So let's go ahead and attack this. Being that we have this nice polynomial form here, we can look at the antiderivative of each term in the polynomial separately. So our first term, we're going to have an x to the fourth power here. If we take the derivative of that, it would be x to the third because we're subtracting 1. So I need 4 times some number is going to give me 2. All right. So I know some students, they love to try to do this in their head, and it can get confusing sometimes. You can grab a calculator and do some things. Don't be afraid to do a little side work if you need to. So I need 4 times some number that's going to give me 2, right? So let's write that down as 4 times n, which is some number, is going to give me 2. And then we could just solve this like an early algebra problem, like divide both sides here. We're going to have that this is 2 over 4, which is a reducible fraction to 1/2. So the coefficient here is going to be 1/2. So 4 times this, right? This will be 4 divided by 2, which is 2. So that works. So you can do that side work. Now, many of you maybe thought, well, that's easy. Like I saw that from the beginning. But, you know, for those of us that didn't see that, it's not a bad idea to have some side work here and to know we can do that side work. All right. So this is just side work over here. The next term that we're going to look at, we're going to have x cubed here. And we need something times 3 that's going to give us 5. Many of you learn to just take this value and make a fraction out of it with this exponent as the denominator, and that's perfectly fine to do also. So that's another technique. That would have worked over here as well. This is going to be 15 over 3, which reduces to 5. Okay, and then lastly, I need an x here. All right, the exponent here is really 1. We don't normally write it down there. So I need 1 times something is equal to 8. Well, that's just going to be 8 here. And then we are going to evaluate this from 0 to alpha. All right. Now, the nice thing about the second half of this, it is going to go to 0. What's the first half of this going to be? Well, we're going to plug in alpha everywhere that we have an x. All right, I'm not writing down the second half of this, but if you plug in 0 here, this goes to 0. If you plug in 0 here, this goes to 0. And if you plug in 0 here, it goes to 0. So we're subtracting 0 from this. So this is what we end up with. Right. This was a definite integral, so I did not put a plus c here. All right, so this is our result. Now, what would happen if you go back to this now and somebody says, okay, we need the same integral done, but now instead of having a variable here, we need this to be 5. Well, in that case, you can go straight to here and plug in 5 for every alpha, and that will be the result of your integration. You don't have to redo all the other work. Now, there would be an adjustment that you need to make if you, for some reason, would need to adjust this lower bound. We had not accounted for that being anything but 0 in this case. We could have established that this was some variable also and come up with a formula for this integration where the lower and upper bounds were variables as well. But in this situation, we were just given that the upper bound was a variable. One of the ways that you might actually see this in one of your calculus classes is if you had taken the time to derive the formula for the area of a circle or the volume of a sphere. You can let this run from 0 to r, where r is the radius of your circle or your sphere. In that case, it gives you a very useful formula that you can take outside of calculus and give to people, say in high school, who don't have a calculus background, and have them use that as a general formula for area or volume. And that's very much a modern way to get those formulas. I hope this has been interesting to you. Perhaps you can find some calculus in your area of the world to share with someone else. Cheerful Calculations.